Abrupt climate changes are not uncommon, and as we will learn later today, can have a profound impact on human society. The top panel shows changes in temperatures that have occurred since the last deglaciation. Time is on the x-axis and temperature in Greenland is on the y-axis. You will note some rapid and large temperature shifts immediately following deglaciation, which we will discuss further in a minute. And then a more stable period of temperatures. However, warming during the medieval climate anomaly allowed the Norse to expand to Greenland and North America, but cooler conditions during the Little Ice Age led to a collapse of these new colonies. The lower panel shows drought through the Holocene. A very dry period about 1,000 years ago is believed to have pushed the Mayan civilization in Central America to collapse. We will look at both of these examples more towards the end of this lecture. How a system responds to a forcing is variable. It can be linear or muted, where the system just gradually changes in response. Or it can be nonlinear, that is, abrupt and surprising. In some cases, a system will show very little response until a threshold or tipping point is crossed, causing the system to change swiftly and unexpectedly. This is a nice illustration of a tipping point. If you have ever played around in a canoe and tried to tip it, it isn't that easy. In this case, you are the forcing and the canoe is the system. As you rock back and forth, the canoe stays upright until you cross a tipping point. Then the canoe system overturns and is in a new and very different state. We can use archives of climate to learn more about abrupt climate change. Today we will focus on two examples from the Paleo Archive, the Paleo-Eocene thermal maximum and the Younger Dryas. What is the PETM? The PETM, or Paleocene-Eocene thermal maximum, is a period of exceptionally rapid warming that occurred about 55.5 million years ago. It occurred during the Eocene, which is generally a warm period. We know about its existence from the marine record. The PETM has been extensively studied because it provides the most recent analog for modern rapid greenhouse-driven warming. This slide is oxygen isotope data from marine sediments, and in particular from forams preserved in marine sediments. It shows that the PETM is characterized by a rapid increase in temperature, shown by the red circle. The rise of temperature was between 4 to 10 degrees Celsius over approximately 20,000 years. The data here shows what's referred to as the carbon isotope excursion. Carbon isotopes, that is the ratio of carbon-12 to carbon-13, reveal a dramatic decrease during the PETM, which scientists report as an increase in carbon to the atmosphere. This is supported by a dramatic decrease in calcium carbonate being deposited in the ocean sediments, as shown on the plot to the right. Scientists agree that carbon was released into the atmosphere, but continue to investigate the rate and release of carbon and its source. This diagram shows three data sets: delta C13, delta O18, and calcium carbonate. The delta C13 represents carbon dioxide in the atmosphere. Delta 18O represents temperature, and calcium carbonate represents ocean acidification. Decreases in the deposition of calcium carbonate synchronous with warming temperatures and increased CO2 are indicative of ocean acidification. The decrease in calcium carbonate indicates that calcium carbonate is being dissolved as it falls through the water column before it can accumulate on the ocean floor. This happens with an increase in ocean acidification. Although several possible explanations have been proposed for the data shown in the previous slide, and in particular the increase in carbon dioxide in the atmosphere, including kimberlites, which are kind of like an underground volcano, volcanoes, comets, burning of peat, and the final methane hydrates. Most of these have been refuted through hypothesis testing. The most likely cause seems to be the release of methane from the deep ocean. However, this is still hotly debated. Because of high pressures and cooler waters in the deep oceans, some gases are trapped or frozen in calthrites, just like the one shown here. If the deep ocean warms, gases like methane could be released from these calthrites. Although we don't entirely understand what caused the PETM, we do have information about its effects. Effects included a loss of deep sea organisms, expansion of marine organisms in surface waters, a loss of archaic mammals such as the Tetanodius primus shown here, and an increase of modern mammal species. Scientists continue to intensely study the PETM because it is the most recent time in the past when carbon dioxide increases to the atmosphere were similar to today. Scientists hope to gain a better understanding of our future by studying this period of time. Another period of rapid climate change that scientists are studying intensely is the Younger Dryas, or YD. Unlike the PETM, the YD was not caused by increases in CO2, but by changes in orbital variations and accompanying feedbacks. The YD is an abrupt cooling that occurred between 12.9 to 11.5 thousand years ago. It is named after the Arctic flower Dryas interfagolia, which is shown here on the right.